Thank you for your attention. I'm going to talk about the high-resolution spectroscopy to uncover the nature of luminous variables and Wolf-Rayet Nebulae. So my real point is the nebulae. I'm not going to do a lot of stellar spectroscopy, but nebula spectroscopy. When I looked at the program and I figured, well, I'm lucky for one and unlucky for two. I'm lucky this is not the after dinner speech, but it's the after lunch speech. So for one thing, it's bad because after dinner speech, you just have to do a little bit of philosophy about life, astronomy, and wine. In the after lunch speech, you have to make sure that the people who are heavily loaded with lunch are sitting there and are ready to fall asleep. Yeah. So I need it to be very energetic and interesting. So let me give it a try. The topic I have is on massive evolved stars. Both luminous variables and Wolf-Rayet stars are massive evolved stars. So first to get me a pointer. To get you in the mood what I'm talking about, I did bring around a classical yep. I did bring along an HR diagram, so temperature versus luminosity, and different evolutionary tracks of massive stars, because I'm talking only about massive stars here. I don't do it below 8 solar masses. So these are various paths, stars after the main sequence, which is here, evolved before becoming, as usually for massive stars, a supernova. You can see color-coded are 3 completely different weight. All those between 2040 and so on, you have to interpolate how they look like. These are just 4 examples. So let's follow me through the lives of massive stars. The very low mass stars, below 22 solar masses, are having, after the main sequence phase, becoming red supergiants, maybe for a short time blue supergiants. Red supergiants turn back into this phase and become supernova. Those above 22 solar masses, in red coded, are red, or they start one way or the other depending on the mass, become luminous variables, Wolf-Rayet, and finally enter supernova. The more massive stars never become red supergiants, will become Wolf-Rayet, luminous variables, Wolf-Rayet, and supernovae. And this is wrong. This is a blue supergiant. Those above, and this is very new, because this is actually, for the first time, this is including mass loss of a star and rotation of a star, which was important. And the very new one is that these stars become Wolf-Rayet and end as Wolf-Rayet only. So this is what happens with massive stars in their life. So what is also important is the wind velocity. I want to get a nebula. And how do you make a nebula? You need material, and this is former star material. So in these phases, on this side of the HR diagram, if a star is hot, actually this is only true for massive stars, I said. So in this phase, the winds are fast. In this phase, the winds are slow. Also, this is very thin wind, this is very thick wind. Here you lose very slowly, but quite an amount of mass. So, also, what is the result from this is, if you cross the wind velocities, if you cross the HR diagram, the wind velocity changes. So naturally, for nearly all of those here, a few here, but most of all the stars, the wind velocity changes within their lifetime. So, as I said, I talk about LBVs and Wolf-Rays. This is where they sit. I said, here you become an LBV and at the end Wolf-Ray. Here you become an LBV and the end a Wolf-Ray. So the wind-wind interaction is the deal to produce a nebula. You have a fast wind, you go in the LBV phase, or on this side you have a slow wind. Then they go back to the Wolf-Ray phase or the hot phase. Then you have a fast wind. What you do is, in the cool phase, you accumulate a lot of material around the star. Then you go to the hot phase. Then the hot fast wind smashes into the older material that's still close to the star. It compresses it and it forms a nebula. So, by the way, what is an LBV? Here a short note how everything started. It started with Pickering in 1897, who said the fifth star is variable and has a range of rather more than a magnitude in its variability. And it was not as one of those typical ones they already know, like Cepheids. It was not regular variable. And a few years later, Buchanan in 1922 and Max Wolf a year later also found some of those stars. And these are irregular variables. This is how the first word about these strange stars appeared. They were, especially Leonard, Hubble, and Sandwich, were searching for Cepheids. They wanted to determine distances, and so they were looking for Cepheids and regular variability. And in their papers, they figured that, well, we have those, but in our sample, we have also a couple of irregular variables. This was the one Hubble and Sandwich noted. So these all together were, we had the irregular variables, the luminous variables, Wolf's variables, Sandwich, and Hubble Sandwich variables. These were the original identified variables. And finally, in 1984, Peter Conti, at a conference said in his talk, I shall refer to the non-Wolf-Ray, that's what we are, WRs, or other hot stars as luminous blue variables, or LBVs in my talk. This was the first day, I don't know what day it was, but it was the first year this term was initiated. And it has a definition as precise as a scientist wants it. It's just non-Wolf-Ray and other hot stars. So, if I want to send you to a telescope and measure stuff, you would have completely great idea which star to look for. So it's the first and one and only definition, and it's a rather precise definition, with a big smiley, of course. It did exclude classical main sequence O stars, it did exclude the Wolf-Ray stars, but that's it. It restricted the sample to luminous or massive, so it's not a big deal. We've got a lot of blue massive stars, blue and hot stars. It's also not a big deal given that we are talking about massive stars, so they're already very blue, and it restricted them to variable. This seems to be a big deal. So it included the already known as Hubble Sandwich variables, the star variables, and the Piscini type stars. They had been known by then, and actually all of these three types are now known as luminous blue variables. So, go back to the stellar evolution tracks from the Geneva models. We have them. This is a plot with, again, these tracks, but now in dots, you can see the position of LBVs. AG car, R127, HR car, and so on. You will see later why we have two positions of those stars. They are the same in luminosity, but they change in temperature. So, let's talk about luminous. Oh yeah, as you've seen, I did bring along the original plot for LBVs. This is a plot by Roberta Humphries and Chris Davidson. I took this picture when I was a postdoc there. So I went to the Humphrey-Davidson limit, and they figured that when they plotted a lot of stars, this is for the Milky Way, they figured this region here, the stars are not found. From first sight, looking just at the nature diagram, why should there be any cool luminous stars? Today we know from the tracks I showed you that this seemed to be a zone of avoidance for massive stars, and one reason is that close to this here, they draw a line and said, okay, above this limit, which is now known as the Humphrey-Davidson limit, there seem to be no stars. And if we go back, we can see the Humphrey-Davidson limit is exactly fitting to the stellar evolution models. They fit, there seem to be no stars, or I have to be honestly to say, there seem to be stars only for a very short time, because stars seem not to evolve or stay here in this region. So, now we have to clarify variable. These stars are photometrically variable. This is AG CAR. It's a light curve from 1989 to 2000. And you can see the visual magnitude changes from faint to very bright, back to faint. So this is a change in 10 years roughly, from faint to bright. At the same time, Ottmar Stahl, who made this analysis, took spectra, and he could see that now it's here from 1989 to 2000, again the 10 years, the spectrum changes dramatically. You have the spectrum, these 30 years it looks similar, here it's completely different, and this one looks more like this one. So they are, first of all, they have photometric variability, but they also have variability of the spectra. So, and what I forgot to tell is, at this point, you do have a hot star. You can see helium-1 lines, iron lines, helium-2 lines, I think even. So in this phase, the star is hot. In these years, the star is cool, and this year it became hot again. So now let's compare to the photometry. This is very, very hard transparency, because now your left eye has to be rotating 90 degrees. Because here I rotated the light curve to match the timeline. We have the star in a cool phase. And we have here visual magnitude. So a cool star, a hot star, has not much flux in the visual. It has most of it in the ultraviolet and the very blue, but not in the visual. So it's faint. This region, the star is a hot star. Wait a minute. It is a cool star, and the cool star emits a lot in the visual magnitude. Then it turns back to a hot star, and again, there's not much in the visual. So this is a combined. Yeah. So this is a coupled variability. The photometric variability is caused by a change in the spectrum. Because it's cool, it's bright, because it's hot, there's not much in the visual coming out. So, and this, going back from cool to hot and back to cool, is called an S-star variability, because S Doradus were the first to be observed to show such a behavior. So it's also called an S-star cycle. So hot star, cool star, hot star is a coupled change of the spectrum. First you would say, okay, the star changes its temperature. These are 10 years. A star cannot change its temperature by so much in 10 years. What it actually does is the spectrum of a star originates at the photosphere of the star. And when the star it inflates its radius. In inflating its radius, it changes from a hot star because now the photosphere is larger, is at a different position, so it appears as a cool spectrum because it has inflated its radius. It's not a real temperature change, it's just a changing of the photospheric radius and therefore the spectrum. In most cases, the variability in the S-star cycle is irregular and has timescales of years to decades. Here it was 10 years. So, and this is the reason why I showed two positions of the LBVs for some we know them. You have the visible phase spectrum, the hot star, it's on this side the HO diagram. Then this is again AG current, the two positions during this 10-year cycle. And then it goes to the visual bright phase cool spectrum on this side. Unfortunately, as you will see later, this is called the LBV and the LBV in eruption. In eruption because this is physically very bad. You should say large radius phase or something. So. And as I said already, for LBVs, this is a way to produce fast wind, slow wind, fast wind. And this interaction of the two wind phases can produce LBV nebulae. So, again, we have the LBVs in the HO diagram. Security advice. Don't leave your LBV unattended. It might erupt. It might show a giant eruption like Eta Car. Eta Carinae had a giant eruption in 1843, but so suddenly, within a year or less, erupted and had a very bright emission. It was the brightest star after Sirius on a total night sky. Afterwards it declined, but... So, what is a giant eruption? Well, a giant eruption is one spontaneous event. We have no hint that it's happening, it's just spontaneous. No indication in advance that it could happen. Increases luminous up to 4 magnitudes. We have a couple of examples for sure. Let me get this mouse out. And Eta Car had one, which we've seen that before. We have P Cygni had it. We have supernova 1945J and supernova 1961V. Here the people thought they were supernovae because it was such an energetic and bright event. They noted this must be a supernova. This here, for instance, is a light curve of the supernova 1961V. So it's so energetic. But afterwards they figured, what? Moment, the star is still there. So it was no supernovae. These two are for sure no supernovae. And the giant eruptions, I had some energy comparison. Giant eruptions versus supernova energy. The radiation energy is 10 to the 49 and 10 to the 50. The kinematic energy is 10 to the 49 and here 10 to the 52. What is not, what I cannot compare because giant eruptions don't produce neutrinos, and we know that supernovae do produce a lot of neutrinos, is the 10 to the 43 urge of neutrinos from supernovae. But otherwise, these are very comparable events. One problem is actually that with all those supernovae surveys right now, there are even more and more. Supernovae find now many events that are looking like supernovae, but for one or the other reason, not completely supernova spectrum, less bright than a supernova and so on. So they are called supernova imposters. For those who don't know what an imposter is, I have a small sketch. The mouse says to the mouse, "You are an imposter." It's somebody who looks like but is not what he's telling you he is or it is. Indeed, some of those supernova imposters are candidates for giant eruption LBVs, but this is a one-way street. A giant eruption will look like a supernova imposter. We just seen this, a couple have already been identified as supernova before. But not all supernova imposters are indeed giant eruptions. There can be many other events. So it's a one-way street. This is important to remember because many people write like, this is a supernova imposter, it must be an LBV. No, I don't want it. Not all of them are true. So, one way is during a giant eruption, the star ejects eventual material. Here is a light curve Eta core. This is what came out of Eta core. This is a contour image of the HST image, plus of the inner part of the nebula. And you can see in the outer region, there's even further material. And this is in total what estimates about 20 to 30 solar masses ejected. Can you imagine how much must the star have? So, let's go back to the definition. A couple of years after Peter Conti's first definition, Bruce Bohannon said, "Remember what is said about ducks. It may look like a duck, walk like a duck, but it's not a duck until it quacks." So it may look like an LBV. What is it? Look like, walk like, but it's not LBV unless it has shown either a star cycle or a giant eruption. So the variability is the big clue, but now we have a way to define an LBV. An LBV can look like an ordinary blue supergiant or even a coolish supergiant, but is not an LBV. It looks the same, but only defining an LBV needs you to find one of these events. A star variability or a giant eruption. Only then I can come and put a sticker on and say, "Welcome to the club of LBVs." Okay. One problem we have is, this is nice, but I want the physics. Why do we have a giant eruption? How do we produce an S-star cycle? So far, it's not completely clear or known what is the astrophysical mechanism behind it. Most likely scenarios, most possible scenarios are for the S-star variability, so-called kappa mechanism. Kappa is the Greek short for the opacity. This is a way to measure the energy transport or the photon
interaction.
What?
Interaction. Interaction of the photons with the material.
With the material. Transport, photon transport. How fast do the photons get from the inner to the outer? If you suddenly block this energy of photon transport, you would heat up a certain part in this, you would heat it up because the energy and photons and temperature is not transported outwards anymore. You produce a certain region where you build up pressure. When you build up pressure, what happens is the pressure rises, and by rising the pressure, you can enlarge the radius. So it's just a blockage of transport energy or photon transport that starts to increase pressure and therefore radius. The problem is this might be a similar idea for the giant eruption, but at a deeper layer. if you have this Kappa mechanism in a deeper layer, what you produce is also pressure increase, but because there's so much more mass on top of it, you cannot enlarge the radius. So the pressure builds up further and further and further, as long as you have such a high pressure and force that you completely inject everything above you. And this would be a giant eruption. The problem is, these are two nice, good scenarios. They sound great. We just don't have the proof. Neither theoretically nor observationally, if that is indeed the case. So, but I want to talk about nebulae, because they're so dear to my heart. An LBV nebula, as I already indicated, can form from the hot, slow wind, the cool winds interacting with each other and forming nebula. Garcia, Segura, and McLeod had already first calculations, hydro calculations, to show that this works. The giant eruption, as I just indicated, might just be forming by layers being ejected. The image I showed about Edakar is not wind interaction most likely, but just ejection of the outer spheres. So, how do they look like? This is my collection of LBV nebulae, and they are scaled. This is 1 parsec. Many of you know the famous homunculus from Edakar. It's just that tiny. So one homunculus is as large as some clumps in this one, only. And they're not very large. You can see a parsec, it's not much more than a parsec. And you can also look at the shape of the nebulae. This seems to be more or less round. This is very round. This is round. This one looks like a triangle. It's completely irregular. But given this guy sits in the middle of 30 Doradus, I don't want to. You have so much massive turbulent material around this one. Whatever forms the nebula cannot stay spherical. So, average size is just 1 or 2 parsecs. A few spherical, so far 1 irregular. They are very bright in nitrogen too. This has to do with the hydrogen burning that is happening in a CNO cycle. Because it uses the CNO cycle, nitrogen is enhanced. The reaction from nitrogen to oxygen in this cycle process is very slow. So if you look at 1 day, everything happens in your cycle until you come to nitrogen. And then the decay to oxygen takes forever and a day. So when you look at the abundance, you see a lot of nitrogen. And this material was brought up to the upper layer of the LBV and then incorporated in the nebula. The astonishing is that there are many, 50 to 75% bipolar nebula. When I started this business, I worked on Edakar. One day I looked at HR, and it seemed I had very bad eyes or very good eyes. I had this fascination. I said, this one looks alike. This one has a blob here and a bubble here, just like here you have a bubble here and a bubble here. So I went to the telescope, took 2 spectra, and it was 2 bubbles. Yeah, it really showed, the 2 spectra showed that there are 2 different bubbles. This is just very faint here, and here is also very faint emission, but it's 2 bubbles. For some of them, by the way, I wrote the paper, and I told them, I wrote in the paper what is true, what is still true, that the phase of a lifetime of an LBV is 25,000 years. This is about true. I got back the referee report and the referee said, no, the lifetime of LBVs is much longer. It's at least 1/10⁴ years. Yeah, 25,000 and 10⁴. So, for a couple of them, HR car, AG and HR car, we at least know that they have fast rotation. So fast rotation might be one clue to produce bipolar nebula. It gives you an additional force, and it gives you additional symmetry axis where the wind might flow. So. Then I looked at AG car. This is the first and for a long time best image made 1950 by Thackeray. The image Ottmar Stahl made looked not much different than this one. Even the AGC image I looked at doesn't show too much difference. It's kind of box. You can see here is a little bit two rims perhaps. So AG car is, if something like this actually exists, and I don't think it really exists, is the most typical, currently best studied LBV. Nevertheless, I was so keen while observing. I made first this image and it looks still similar, but I increased my exposure time. And suddenly you can see here this is overexposed more or less, but there's much fainter material. This is now a composition of these two images. You can see the central classic nebula, but there's much more to it. With this longer exposure, I doubled the size of the nebula from this diameter to this diameter. And I could show that there's an additional emission stranger here up on the top. Then I took some high-resolution long-slit Echelle spectra. You can see the nebula here had two long slits going along from here and here. And this is the slit going through 7. The upper 7 is going through here, roughly. It's a little bit south of the central star. And this is how the spectra look like. What you have is the kinematics of the gas of the nebula. So to get you into the right mood, first of all, what you would expect. Now I need two hands. If you have a bubble and you measure the expansion velocity of the gas, you only measure the radial expansion velocity because you get a spectrum, not the proper motion. The expansion, however, is symmetrically, radially, in all directions the same. So if you measure at this point your expansion velocity, the radial component is very low, if any, because the expansion goes in this direction, the radial velocity vector is very low. At this point, really towards you get the fastest velocity, and here again you get it very low. So what you would get is two so-called expansion ellipses. You have here at the position of the star, you have the nebula in front of you, you get the largest. So you get the two measurements in velocity, and what I get is really two expansion ellipses in this slit. It turns out there are two bubbles. It looks like an hourglass, like Eta car, except you have a pole on, or slightly tilted only. there are two bubbles, and the two bubbles are here, red shifted bubble and a blue shifted bubble, one in front, one in the back. And you can measure the expansion velocity of each bubble, which is 27 and 25 kilometers per second. More distance a little bit, radius a little, 1 arc second larger. But the idea is, what I wanted to tell with this complicated transparency is, it's really bipolar. This is not, as it originally looks like a box or an ellipse. It's bipolar, you're just looking pole on onto it. And this additional emission to the north here appears here also with a faster velocity, but it is connected to the bubble in the back. So the best interpretation is this cone-like structure is part of a bubble, an outflow from the backside bubble. And while flowing out, it has a faster velocity, so this is an expansion of, or movement with 100 kilometers per second and not only 30 like the bubbles. So the best model is an outflow from a superimposed by image showing clear, it is also imposed, but it has no clear rim. So it's not a confined bubble, but it's gas that moves out of the bubble. So, we're back at the question LBVs. After studying a lot of LBVs and getting a lot of bipolar LBVs, everybody started kidding about when they saw me. You got another bipolar? You got another bipolar? And every star I looked at closely, I made bipolar. So, after that I turned and said, well, after the LBV phase, the stars turn into Wolf-Rayet. And I knew already there are a lot of Wolf-Rayet Nebulae. So, I looked and thought, well, there are many spherical, elliptical, multi-shell Wolf-Rayet Nebulae. They are somewhat larger, they're 40 parsec in size typically. And so they're larger and more spherical. This is okay because slow rotation is expected, because on the long way from the main sequence of the Wolf-Rayet phase, these stars have lost a lot of wind, and each wind takes already with them the rotation, the angular momentum. So they're not rotating very fast. So, and I scratched my head, well, I know a lot of Wolf-Rayet Nebulae. Where the hell are there any bipolar? I've made everything bipolar. I said, hey, I really scratched my head. Where are bipolar? Why shouldn't they be bipolar? Planetary nebulae are bipolar, LBVs are highly bipolar. So I keep looking around and I found one. M1-67 around WR127 is a bipolar one. You can see it barely, I don't have a better public image, but it has a bubble on this side and a bubble on this side. And so it is WN8 spectrum, but I looked at the literature, and starting to look at the literature, I was lucky I became also the referee of a paper about this topic. And it has a nitrogen overabundance, bright nitrogen 2 lines. It is rather small, and most of it, let me think, this is probably not a Wolf-Rayet Nebula. This is an LBV nebula with a central star. This is an LBV that just moved from the LBV into the Wolf-Rayet phase. So it just turned the Wolf-Rayet star, therefore the Wolf-Rayet spectrum, but the nebula is a remnant from its LBV phase. It has blown and created the nebula before becoming a Wolf-Rayet star. So, when I looked again at my list, I looked again at my spectra, which I've forgotten in the drawer. But there was one I always was interested in, was HE Henais 3-519. It looked so boring and round to me. And I decided to look at it in close. Went back to the data. Here is an HST image of it. And I said, well, it's classified WN11. It's an LBV in its hot phase. It has, with 2 by 2.5, one of the largest. It is the largest real LBV nebula. So I looked at the spectra again by mapping. And as you can see, I found the expansion ellipses in the slit spectra. And if you look carefully, there are two. It's not just one, there are again two, shifted by a slight bit. So again we have at the central position two, it's not unlike A-Jopper, two shells superimposed on each other. So again here you have a bipolar component. So the kinematics from the spectroscopic bipolar structure, it's the largest in size, and the bipolar ray might just be fading because it's a Wolf-Rayet star already. In the hot wind of a Wolf-Rayet star, Wolf-Rayet stars have the fastest wind of all massive stars. It ran into this old bipolar LBV nebula and blew it up, and the bipolarity is weakening. So my idea here's a new addition to the bipolar LBV nebulae. But already on transition to the Wolf-Rayet phase. Kinematics in the bipolar component, due to the hot phase blow up of the nebula inflation, bipolarity is fading, as I said. So here we have probably an LBV soon becoming a Wolf-Rayet star. So we have those who just always keep saying M1-67 retired already to a Wolf-Rayet, and this one is about going into retirement. So my lecture was that the connection is there's a transition from LBV to Wolf-Rayet phase is seen in two stars. They are just going from one place to the other. LBV Wolf-Rayet stars have, if I believe this is not a true Wolf-Rayet nebula, but old LBV nebula, have so far no bipolar nebulae. Is fading. This one is being in the LBV phase, left it, and this one is going to. So this might be the missing puzzle for these two phases. There's another interesting part that I did not make a transparency of, but in recent in the recent years, measurements of the masses of Wolf-Rayet stars, and this is mass in the Wolf-Rayet star phase, not at the beginning of the star, show that these stars are less massive as they should be. Calculating just the winds during the main sequence phase and Wolf-Rayet phase, it turned out they should be less in mass as they observed. So my claim is maybe all of them have gone through the LBV phase, because in the LBV phase the mass loss increases highly and removes a lot of mass, so that maybe the LBV phase is mandatory for those Wolf-Rayet stars we see now with the low mass. I cannot prove it yet, but this is my current interesting project. Do all massive stars go through the LBV phase before becoming Wolf-Rayets? Or at least a certain path. It's not true, of course, for those very massive stars that become Wolf-Rayet immediately after the main sequence. So my is Only high-resolution spectroscopy, the one I did, were able to study the kinematics and reveal the bipolar nature of AG car, as I shown, and of Heli 3-519. Only by the spectra we could really say this is not a box and this is not a box really, but is a bipolar structures viewed polon. Also, only by high resolution spectroscopy, kinematics and chemical composition in this case, could unreveal that Wolf-Rayet Nebulae might be old LBV nebula. So this transition these two made and are going to make. So, what telescopes did I use? There are two important ones. It's a 1.57 meter Weiss and it's the 4 meter Blanco. And one last, now comes the philosophical part of the after dinner speech. There is a quote. It is not too much to hope that in the not too distant future we shall to be competent to understand so simple a thing as a star. This quote was made by Sir Arthur Eddington. Attention, in 1926. This is nearly 100 years ago. So, do we? I have two solutions. Either we are still not in the not too distant future, in 2022, or we have to admit a star is not a simple thing. And with that, thanks for attention, and my happy star. Fire when ready for questions.
Very good.
Can you show your initial Hertzsprung-Russell diagram with all these paths, evolutionary paths of stars with different masses?
Yeah.
Yeah. So,
This one or
yeah,
the
the one
tracks?
with all these classifications, LBV,
Yeah.
Wolf-Rayet, yeah, here. I don't see here one category, maybe I'm wrong and it shouldn't be included. There are B-brackety supergiants.
No, what?
B-brackety supergiants.
But B brackety.
So
Yes.
are they, at some
this
point,
is just a spectral.
yes,
distinction.
but these are supposed to be massive stars with luminosities around 5 point something, the log L, and they have dusty envelopes.
Yes.
Ida Carine was considered in the very beginning of studies of all these infrared stars to be a B-brackety star.
Yeah.
So I don't know, maybe in some kind of more recent understanding, we should exclude that category. I'm just wondering where it can fit
The
here.
difference is the difference between a spectral distinction and a stellar evolutionary phase. B brackety is just one type of red supergiants,
Blue.
blue supergiants, that have a special distinction because they show a lot of forbidden emission lines.
Not a lot of, mostly permitted lines, so forbidden lines are just
Yeah.
a distinction. But I think Ida Carine also has them.
I think what Kerstin is probably mentioning that, yeah, there are these colors, but they would be somewhere in the regime in the blue supergiants. So we
Okay.
have a
Yeah.
very specific phase, maybe linked also to binary evolution, which would be in here, but would not be pinpointed to a specific region.
All right.
It's also, I think, what we could differentiate is it an observed class or is it a theoretically? Theoretic classes contain, in most cases, many different observed classes because they show a special kind of emission, or it's like I didn't also, if you would look at the Wolf-Rayet stars, I didn't distinguish between the VCs, the VNLs, so the nitrogen rich, the carbon rich or so, which are also not completely differential because for theorists, these are Wolf-Rayet stars in the Wolf-Rayet phase. This is just a theoretical view. I would have to make a different view for the nature diagram for the observed classes.
I think it would be an extremely interesting point for the E-bracket E-stars if they scatter over a broad range or if they are relatively well pinpointed.
Yeah.
And I think that the last times when Kerstin made the plot and we discussed about it, I think it was not a clear pattern due to the low number statistics.
Yeah, so I think I showed some time ago that the median luminosity is about 5.1, so it's close to the lower end.
Okay.
Yeah. Okay, so I got it. And another question is about Wolf-Rayet stars. So WCs,
Yeah.
carbon rich, they have dusty envelopes. That's
Yes.
definitely. So do they have nebula or not?
VCs don't.
Don't. So dust forms can be observed, but gas, there is not
Yes.
much gas there to show up
That's so
as
nice
a nebula.
because most of the nebulae actually are around WN stars, meaning they are nitrogen rich. What fits to my idea is the LBV nebulae are nitrogen rich. So these stars are already potentially the right version.
Maybe strange in that it's nitrogen rich and they are the ones at the lower luminosity,
Yeah.
not the WNLs at the top.
Yeah.
Yeah, you were talking about the bipolar structure.
Yeah.
Where does it come from? Is it binarity? And is there
Question
some
mark, question mark, question mark.
question mark?
Two ways to produce it. We know for planetary nebula there are quite many double stars that produce bipolar PNs. For LBVs we have, as I showed, for some we have a hint, it seems to be rotation. Because HRCAR and AGCAR are fast rotating stars. But we cannot exclude completely binarity. On the other hand, I know two binary LBVs that actually do not have any nebula. It's not also that not all LBVs seems to have nebulae. So meaning either too few mass shattering in their star cycle, didn't have any giant eruption, or just at the beginning of LBV phase.
Kerstin, maybe you want to comment why rotation leads to bipolarity.
This is because of the how fast should I stretch? I mean, the wind compressed disk model, or so one idea is if you have fast rotating, you produce a disk around the star because of rotation. Then your vector lines of the wind have a centrifugal force, and the vector of the wind velocity, the one on the pole crashes with this side with the other one. And what you form is a density enhancement. I'm not a theoretician, I just know from the paper. And these papers show that there's a wind compressed disk forming. And this wind compressed disk forms, as it says, around the equator of the star. And if you now have a mass enhancement, a mass loss enhancement, it will not go out into the disks because there's already waste avoiding. So the rest of it would go out on both polar sides.
But if the two stars would be binaries and we're looking basically pole on, then we would hardly see any of the binarity because it's probably we're just looking plane on. And we're looking pole-on, so the rotation broadening would be rather small unless we probably wouldn't see any binarity because we're looking plane on.
That is true, but there are limits from stellar interferometry and also high resolution images that there are several LEVs without having a clear binary. There is one candidate, but at least for the timeline of 10 years, it seems not to be. So whatever that means. That would be a relatively wide pair anyway.
Yep.
And
Because
that's important.
the massive stars. So by the way, when you say the very low mass stars and you pointed at 22 solar masses, that's
Yeah, exactly.
yeah.
Yeah, that was an important part because
But-
we have.
So for the very massive, I think the binary fraction is basically every star is expected to be in a binary system.
That is, Kerstin, may I? This
Yeah.
is my favorite topic, or one favorite topic. Okay, there is a very good analysis by the group made a large analysis on the binarity in the 30 radius. And there you can split. There are about 25% single stars, 25% stars in wide binaries, so no influence of evolution. Then there's probably 30% where are close enough, so there will be binary evolution, an important thing. And there will be something like the rest, something like again 20-25%, which are so close that they will merge very fast. But if they merge, then after some instability, they develop as a single star again. So I would say probably 50-50, which is not the probably most of them, well, let's say 70-80% are binaries, but only 50, maybe 30% the binarity would have an effect on the evolution.
Okay.
So that we could interpret from this this famous diagram from this science paper. Try to remember the author now, but
What also is important for the mass is, at the beginning, the predictions, stellar evolution models for LBVs were stars above 40 and 50 solar masses, which made a problem for those guys here. This changed with stellar evolution, including rotation. Only with those we can completely explain that here is a turning back in the stellar evolution. There was a story for supernova 1987A. 1980-78. Here is the importance of the stellar wind. When this supernova went off, all the stellar evolution models said a massive star evolves from the main sequence to the red supergiant phase and explodes there. 1987A went off, and thanks for whatever reason, we did have a spectrum of the progenitor. And the progenitor was, as it's indicated here, a blue supergiant. We didn't fit to the models. The models said they all explode as red supergiants. That's when the theoreticians started to incorporate stellar winds. It was the first time it became important that mass loss of massive stars is important for the stellar evolution. And the similar one is happening now with the rotation. Only with the rotations model could we explain LBVs in this position of the HR diagram. So theory is nicely driven by observations.
which should not mean that binary evolution does not play a role. I think this is just another not fully explored parameter here. As
It's one ingredient, but not the
only the dominating thing.
You showed for one object you showed three different images separated by about 30 to 40 years. Do you see any temporal variation?
Not sure what you're talking about.
Do you actually see, because we now have about 100 years time variation. So
Which
of the
picture do you
memory, you had three. But anyway, yeah.
Yeah.
Do you see
This one?
No,
Not the other
the
one.
last one.
The previous one, yeah.
Yeah.
Do you see variations? Because they are obviously close objects, very big. Do you see variations, or do you see variations in the spectral lines? How those objects evolve?
Well, you see it as I showed you for the S-star cycle, you saw it.
No,
I showed
yes,
AG car.
He is meaning the size of the nebula.
Mhm.
Do we see changes of the size of the nebula? I
No,
think will not be
It's hard to
possible.
get because, at least for these, you have very different filters, you have different exposure times,
No,
and
but
extremely
Kerstin-
resolution.
Yeah, Kerstin, I think the relevant point is this is 5 kiloparsecs and this is 30 kilometers as you showed.
Yeah,
So that is not enough if you don't have HST. Even with HST in 30 years you don't have. You can observe it
for
with
8.
Eta Carina,
Eta Carina,
which is 2
yeah.
kiloparsec and 3,000 kilometers or 2,000
Yeah.
kilometers per second. There you see.
I have a question which comes from the view of the amateur observations. You know that I'm an observer of Piscygni
Yeah.
itself. After your talk, I wonder, does it make sense to observe this star as much as is possible, because that is one of the main intention of the amateur area, to observe this star as much as is possible. But if I see now that we have only long-term changes for Piscygni itself, does it make sense to observe this star so regularly as we did it in the past?
Well, the problem is not definitely long term. You've seen how fast AG car changed. The spectrum changed from hot to cool to hot
Yeah.
in 10 years. Oh, and if you would say you just need half of the cycle,
Within 10 years only?
yeah. We're already here. You can see it. This is from 1989.
Mhm.
That's a spectrum.
Mhm.
And you can see every time you have an error here, is a spectrum taken.
Mhm.
So from here to here, it's 10 years.
Oh, yeah.
From a hot star, you know, 1, 2, 3, 5. Let's go to one further. It's only the spectrum. You can see here, this is 1989,
Yeah.
and this is 2000.
Oh, yes.
So you have here 5 years from here to here.
Mhm. Oh, yes. Yes, against that background, it makes sense.
Yeah.
Okay, my next question.
Some are
is-
even faster. There are a couple of LBVs that make a cycle in just 5 years.
Mhm.
The problem is there are also some who make it in 50. So there is no clear prediction.
Mhm, okay. Good. The next question
That's
is.
one thing you can predict for LBVs. You cannot predict anything.
Okay, yeah.
It's the one clear.
Yeah. Good. Another question is, may you know that also observer for the area of helium-1 6678.
Yeah.
Does it make sense to observe this area?
No, if it's in the hot
If I-
phase.
Sorry?
If it's in the hot phase, it shows up.
Because I couldn't see anything about this line in your investigations. I see only helium 4471, for instance. But what about the importance of 6678 of helium?
Sorry?
Yeah, if you look at the 4713 helium-1,
Yeah.
so this is a weaker line, but on the other hand, it shows the same trend. It's the
Yeah.
temperature trend
where the helium line is in this temperature range relatively sensitive to. So if it disappears at the lowest temperature, is weak in some other steps and gets very strong there. So that the behavior will be very similar there. But you need the LBV in activity. So even, for example, P-Cygni is in this hot phase state since at least 100 years. And we don't know if that changes and on which time scales it will change. So that the problem is really, you can just go on observing and hope that something will happen.
We have to be patient.
Yeah.
Okay, thank you.
I have one more. Back.
I had two questions. If you have a giant explosion, what is the maximum velocity of this explosion cloud?
You mean the giant eruption?
And the second, how long you can see a brightness more than 4 of magnitude?
Well, the first answer is hard, because it can have anything. Eta Carinae, the explosion, we detect velocity as fast as 3,000 kilometers per second in the ejector. At the same time, you find clumps that are as low as 100.
Okay.
It actually is very bright in X-rays, because
Yes,
the 3,000
That's
kilometers
the
per second.
maximum.
Maximum 3,000, maybe 5,000.
Okay.
I mean, what problem is the detection? I mean, from all these 4 I showed you where we know this is a giant eruption, supernova 1961V, 1945J, P-Cygni and Eta Carinae, we only have 2 that do show nebulae, and only the one around Eta Carinae is young enough to give you good, there's 150 years, 160.
There I disagree. You have for the 2 others, they are too distant to
Yeah,
have a
too-
spatial result nebula, and if the mass
Yeah.
ejected is too small, then you will not see the spectral signature of the lines.
And but with P-Cygni, it's the giant eruption was 1600, so we got 400 something years. Where it slowed down already, where it's not more representative for the sharks and the decrease in velocity.
Okay. And how long you can see the great brightness?
Well,
1 week,
Eta Carinae
2
was
weeks?
Eta Carinae was bright
Only
for
1,
5 to 10 years.
5 to 10 years. Yes.
It could be if some of the imposters which we are analyzing, if they are very similar,
Yeah.
this is always a if, as Kerstin said, they come back, so they can have an eruption time for maybe half a year, then having a pause of 2 or 3 years, and then come back again.
Okay.
Yeah.
So that can also happen.
Okay.
It also depends what happens. For Eta Carinae, we know that very soon dust condensation appeared, and this dimmed. So it declined very fast after a while because of setting in of dust formation.
Okay. Thank you.
I have an additional question. Is there for P-Cygni a comparable overview like it for EJK?
Like what?
For this star, is there for P-Cygni a comparable overview like we could see it here?
The nebula or the...
No. That's a spectral overview for instance, for 10 years or 20 years, like this overview of A.G. Gagarin.
The problem is that
P-Cygni.
P-Cygni didn't change much of the spectrum in the last years.
Uh-huh.
It didn't have an S-star cycle. There are even LBVs. There was a Van Genderen, an astronomer in Netherlands. He subdivided the S-star cycle in long S-star cycle and short S-star cycle, below and above 20 years. And he said everything above 100 years he called dormant. So there are actually a couple of LBVs that are dormant. They'll fall asleep. So, the only prediction is the unpredicted for LBVs. It makes them so fascinating, and you don't know when you wake up next morning who went off, what went on in the use of LBVs.
So, good example, R71 in the LMC, which was
Yeah.
pretty boring, and then suddenly it has a giant eruption.
Yeah.
Something like what was 8 years ago.
Mhm.
Completely unpredicted. And is following now the track very similar to Beta Carina.
It all goes a bit back to the problem, what is the mechanism? If we had an idea what is happening, you could say, okay, in this phase, or if something on the outer, in the photosphere is happening, then we can see an Astor cycle, or we can even predict the giant eruption. But as long as we don't know about the physics, we can just keep going, observing, collecting data, and by collecting data, knowledge, and hopefully one day the physics.
What is the luminosity, so what's the fraction of the Eddington luminosity, and what is the metallicity?
Metallicity is completely wide. You have them in the LMC, in the SMC, M31, M101,
It's
Milky Way.
interesting if you go below a tenth of
Yeah.
solar.
Yeah.
They are still there, but they behave somewhat strange.
Yeah.
Metallicity, you mean?
Metallicity-wise,
Yeah,
And what is the level of Eddington limit?
close.
Probably show the diagram, Kerstin.
What? Yeah.
Pretty much from us, the diagram. Yep. So the Humphrey-Davidson limit is very
This
close.
is roughly the Eddington limit, and this is why they turn back. It's actually here. It is Humphrey-Davidson was empirical, as I showed you. They just kept on looking and observing stars, and they figured, why is there a limit? Without any physics, they were observers. And it turns out that roughly at this position in the HR diagram, it coincides with the Eddington limit. So that they turn around here or do eruptions or change something is most likely also because LBVs are close to the Eddington limit. This increases the wind, increases because close to the Eddington limit, your gravitational potential is lowered.
But at the Eddington limit, where the star basically is dominated by a radiation pressure,
Yeah.
You expect variability across the photosphere simply getting unstable.
Yeah.
So is this a counter mechanism then,
Yeah,
or is it a different mechanism?
this is another push to inflate the radius.
But there is variability on a lot of different time scales. So Kerstin
Yeah.
only talked about the relatively long time scales.
Yeah.
But there is
Microvariability.
down to micro variability of 10 minutes or minutes
Yeah.
in these stars. And that is most probably this instability effect if you're close to
Yeah.
it.
But we also have convective core. Could that be some propagation from inside?
Yeah.
The problem is if you do stellar astroseismology of objects like that, how to identify the modes?
You have none.
Yeah, exactly.
One little
Yeah.
thing. Because I was following the theoretical kind of results on that part of the diagram. As far as I remember, the wind compressed disk model was killed in the middle of the 90s because wind compressed disk only works if only the radial force is taken into account. Then Stanley showed that if there is
Yeah.
no radial, then it doesn't work. What's the current state of the model?
Becoming more and more sophisticated models.
Yeah, well,
It even starts with the problem how do you describe wind of massive stars. It's not a smooth blow, they have wind clumping.
I think the one modification at that time obviously is that you have also to keep fun cycle in
Yeah.
in mind. And then you have specific temperatures. So by stability jump, and you have changes
Yeah.
for the wind structure. So that is all there, and I think
Yeah.
we brushed over that a little bit.
Yeah.
But you're completely right.
I think the
This
most
is very
important would, but
simplification.
it's too hard to believe, is the bistability limit, when the wind changes from a polar to an equatorial wind by passing the stellar temperature around 20,000 K. If the star passes this limit, his wind changes from a polar wind to an equatorial wind.
I have two questions. One is, do you expect
Bit louder?
Do you expect LBVs to both show giant eruption and star variability, or one or the other?
So and so. The problem is there is no theoretical way why they shouldn't do both. But we have not observed a star so far to do both. So none of those detected with an S-door cycle has later gone giant eruption. And for those who had giant eruptions, you cannot, from the back, say it had an S-door cycle, because it went giant eruption, you don't have the observations. And it's also a problem of time. You may have a lot of those which are doing S-door cycles now, not having them before. And you have a lot of them where you don't know if they are probably are an LBV because they had a giant eruption. If you had a giant eruption in 900 before Christ, nobody would have noticed, nobody would have seen this LBV. So this one could just sit somewhere in the universe and now do a normal LBV life without a giant eruption. If it had not erupted enough, and why would you see the nebula if there's not enough material? If it just shed like 2 solar masses, a blue supergiant, you would not find the nebula. Keep on looking. That's a simple thing.
And my second question is, did I understand it correctly that your hypothesis is that all Wolf-Rayet stars were LBVs once?
Yeah. The idea I have this hypothesis because of the mass. The current day mass they find, so the mass in the Wolf-Rayet phase, they find, they say this is way too low for a normal life to have just shed so much mass. By the time they spend, if you do not have the LBV phase, you have the red supergiant, the blue supergiant, and the main sequence phase. And if you add the mass loss of these 3 phases, you do not get a Wolf-Rayet star with this mass, with this low mass.
Okay. So you
was probably the one.
Yeah, as I said, this is only not for the very those after the main sequence becoming Wolf-Rayets.
I think for the ones which are the close binaries, because then it was binary evolution.
Yeah, those 2.
Okay, so but you also said that the Wolf-Rayet stars usually have a spherical nebula. So do you expect that the bipolar nebula...
the idea is a Wolf-Rayet star has an extremely fast wind.
Mm-hmm.
So whatever you have as an LBV nebula, you put in the Wolf-Rayet star and you turn on this extremely fast wind. What you would do is, if you have fast wind in all directions, is whatever you had as shape, you can you sphericalize it more or less, because you run in this, you blow it out, because you put kinetic energy into the nebula, you blow it up by the wind. And this changes the morphology to more and more spherical.
Thank you.
Okay. Thank you very much.